Can you enable share screen? All right, welcome everybody, welcome. Well, I'm really glad you could make it out tonight. I'm going to start off, make sure that everyone understands we have to have everyone wearing a mask for this event, okay? Otherwise the school won't let us hold it. So I got extras up here if you need anyone. Excuse me. My name is Brian Jackson. I'm a professor here in the physics department, teach physics and astronomy. You are here attending the first Friday astronomy events. We're very excited to be able to host you again. Those of you who were regular attendees, at one point, we used to host these every month. They were very popular. The last one of these we hosted was literally 2 years ago, almost to the day. March 6th, 2020 was the last one of these we held in person. So this is the very first one we've held in person since then. Yeah, it's very exciting. I'm going to tell you what, it's a lot easier to do this in person than it is to do it virtually. So we're very pleased that you could join us this evening. For those of you who have never joined before, the First Friday Astronomy Events is a monthly astronomy event. We bring in a lecturer who's an astronomer or space scientist, sometimes space journalist, sometimes a space policy person. They come in, they give a talk, about 45 minutes, and we open it up for questions. It's a very interesting project. It's really fun to have people come out and visit with us, especially with the students. This event, all of these events, in fact, are entirely supported by donation. Public donation covers all of this. In fact, many of you probably walked past the room over there and you saw our inflatable planetarium dome. We just bought that. That's brand new. That was paid for by donations from the public. State didn't give us any money for that. You guys paid for all of that. So if these kinds of events are something you're really interested in, you like, feel free to support us. You can visit that website. It's boi.st/give-to-astronomy. You have to capitalize those letters. That donation is basically what keeps this stuff going. It pays for our guests to come out and speak, pays for pizza for our students, pays for planetarium domes. Our next event, let me see here. Our next event, I can do this for everyone in Zoom. So as I said, we're hosting these live. We're also hosting these on Zoom. So these are being recorded directly to YouTube. So if you can't attend in person, you're welcome to attend virtually. Let's see, there's our next event. So our next event is going to be on April 1st. And we're going to have Dr. Aaron Cox from Northwestern University come and talk to us about planet formation. It should be a really interesting talk. So join us for that April 1st, 7:30. Virtually, you can attend by visiting boi.st/astrobroncos live. And that'll take you to the YouTube live stream. And then, of course, we're hoping that we'll be here in person again. So feel free to join us either way. Okay. 1 second here. All right, so that brings us to tonight's event. We're very fortunate to be able to host Dr. Carl Schmidt this evening. Dr. Schmidt got a bachelor's degree in physics from the University of Colorado, followed by a master's degree in astronomy and then a PhD in astronomy from Boston University. He joined Boston University as a research scientist back in 2017 and has been there ever since. He does a lot of really interesting research, and I think you're going to find his talk very interesting tonight. With that, let's all welcome Dr. Carl Schmidt. Just remember to turn it back on.
How does that sound if it's down here?
Can you all hear that?
Yep.
Perfect.
Unmute this. I think I can just minimize it. I actually don't know how to make it go all the way away, though, do you?
No, it'll stay there. It'll stay there.
It's tiny now, at least. Okay, thank you so much for all attending. Which probably isn't right, too.
I think your video is, go ahead and start your video up, because it's not actually started.
Okay. Okay, now we can see. So my goal for this talk is to convince you that this tiny little moon of Jupiter is the most interesting object in the solar system. I really do think that. I study lots of different objects, and this one is the coolest. And it has a lot going on.
Yeah, we're good.
This
Thank you.
picture sure has a lot going on. Are we still able to hear everything okay? Speak up. I will try and get through all of the aspects of this picture in this talk. There's a lot sort of going on where magnetic fields are interacting with moons. But this schematic provides an overview of all of them just as a background slide. So here's this moon Io, is the first of 4 big moons of Jupiter. Galileo discovered them shortly after the telescope was invented. He's kind of the first person to point the handheld telescope at Jupiter and discover these 4 objects, the Galilean satellites, moving around. And the first one is Io. Don't know. Advance. Okay, so it's a volcanic moon. There are active volcanoes on this moon. Lots of them. 200 plus were mapped by the Galileo spacecraft. And because the moon doesn't have a whole lot of gravity, those volcanoes generate really large-scale plume structures. So this is 1,800 kilometers in diameter, or in radius, sorry. And then the height of that plume is going to be about 100 kilometers or so. So this is much higher than volcanic plumes get lofted in Earth's atmosphere. It's a substantial fraction of the size of the thing.
To share your screen, 'cause it's not. Doesn't seem to have your video screen shared.
Okay, technical difficulties. One moment.
Sorry, guys. This is what you're trying to show right here, right? That's what you're showing.
Oh yeah, so it's the PowerPoint.
Now you're. See, now it still shows your video. Interesting. So maybe we can't do this. Sorry, guys. No, it's still showing your camera and not your screen.
Okay, give us just one moment to try and sort it out here, because we want people online to actually be able to see this.
Sorry, everybody online. We're trying to help you. That's weird. Okay, let's see. Yeah, stop share. Let's just share screen. Yeah, see, it's still showing your camera. So I don't think there's anything we can do about it right now. It should be sharing your screen, but it's not. Okay, that's fine. You go ahead.
So we've got these plumes lofting material from Io's surface high up into the atmosphere, creating canopy shocks at the top of them, and then raining that material back down. And this forms these sort of pockmark looking things. That circular ring is where all of that material has fallen down to the surface of this tiny moon. And you can see that's, you know, a substantial fraction of just the whole map of the planet mapped out in longitude and latitude. And then there's a lot of yellow color here. That yellow is from sulfur dioxide. It's a smelly moon. Sulfur dioxide is what makes hot night smell, and it gives it that sort of gross yellow color. So it sort of looks a little bit diseased. And we've got, in addition to active plumes, lava lakes. This is called Loki Patera, and it is a lava lake that crusts over about for a year and a half or so, and then that crust gets heavy and it sinks, and new hot lava comes to the top and fills it in. So this is a surface that is being repaved right before our eyes, right? We're building new landmass in Hawaii, but that's a small scale here on Earth. This is global landmass rebuilding through active volcanism. Now, in terms of material, there's not a whole lot of gravity to hang on to this stuff. And so we have a lot of atmospheric escape. We're losing about a ton per second. And that has sort of big consequences for Jupiter as a system. But we don't know what drives the atmosphere. We're losing a ton per second. We need to supply a ton per second. And is that supply coming from sublimation, where the surface is just warm and it's evaporating off? Or is it coming from direct lofting from these volcanic plumes? That's an open question. We don't know whether the volcanic plumes, when they get hit by electrons and make pickup lines, they supply Jupiter's magnetosphere and fills up this big structure, but we don't know whether the supply is coming locally from regions in Io's atmosphere, or is it coming from like really large scale clouds that are orbiting Jupiter with Io? Is that a local source or a large distributed source? So there's some active questions that we can talk about here, but they're still unresolved. I seem to have. Okay. So in the infrared, hot things light up, right? So this is Io's day side, where it's just warmer, around 4.78 microns, as seen from the Juno spacecraft, which is in orbit around Jupiter right now. And this is Io's night side, where you can really see all these different little volcanic hotspots glow in the infrared. And each one of them has a fun name. And all of those names have kind of interesting, cultural origins to them that are kind of similar to the names that we have for a lot of the volcanic structures in Hawaii, and the terminology on the Galilean satellites gets interesting. So that's smelly atmosphere here is at sort of a tipping point. The surface temperature of Io is somewhere usually in here or so, maybe 130 degrees Kelvin is kind of a good estimate. But if you drop that temperature just down here, down to Io's night side, where it gets cold, the surface pressure should follow this line, and that's going to drop 6 orders of magnitude. So imagine if Earth's atmosphere collapsed by a factor of 1,000,000 on the night side. If our atmosphere is sustained by sublimation, as opposed to active supply by volcanism, that's the expected result, is that we're going to collapse Io's atmosphere out on the night side. And when you cross through that transition, you sort of hit interesting number densities and pressure levels. So this is the pressure level at which ions can penetrate through the atmosphere all the way to the surface. And then that kicks up its own atmosphere. This is the pressure level of the exosphere, where particles in the atmosphere are no longer colliding with one another. It's a collisionless gas. And so that has a totally different behavior. So it has kind of this cool range of possibilities when we go from the day to night side of Io. And when we have a really dense atmosphere on the day side and no atmosphere on the night side, but of course we try and fill that in with wind, right? So this predicts really strong winds on Io. And if we're locally enhancing those with volcanic hotspots, we have localized atmospheres around each one of these volcanoes. And the best way that we can study this effect isn't by looking at Io's night side, because that's kind of hard to see, right? We're out here at Earth and Io's at 5 astronomical units or so we can't really see the night side. But we do have this cool trick where we can look at Io and Eclipse. So that's the limb of Jupiter right there. This light is infrared light coming from the moon Io. And that little dot right next to it is another moon called Amalthea that's in full sunlight. And when Io comes out into full sunlight, it's going to get much, much brighter. That's reflected sunlight bouncing off the surface of Io. So what's causing this light when Io's in Jupiter's shadow, when it's fully in eclipse? That's volcanic light that we're seeing in the infrared. It's just the surface temperature of Io that is heated up by volcanism. And the volcanoes aren't as hot as they are here on the Earth. Typical temperature is a few hundred Kelvin. It's about as hot as your oven, maybe 500-ish Kelvin, something around there. So we've got this cool geometry where we can do experiments where we sort of switch the lights off and we're able to see volcanoes that we're not usually able to see because they're swamped by all that scattered sunlight. But we can also study how Io's atmosphere changes in eclipse when you switch out the lights. And that's very easy to do in the infrared because Io is self-luminous, right? We can see it here. It's very hard to do in the visible and in the ultraviolet because it's hard to point the telescope, right? It's a dark object that is moving with respect to the background stars. And it's pretty tiny in order to actually track it on the sky. So that experiment hadn't been done until recently. Let's see if I can minimize this. I don't really want this showing up. Don't actually know if I can make this top portion smaller, but we can live with it. So how does Io's atmosphere respond to eclipse? Well, the infrared's kind of nice because you can look at the thermal flux. This is at 19 microns coming from the surface, and thermal flux is sensitive to temperature. So you can watch temperature go down from about 130 down here to 105. And that happens very quickly after ingress into eclipse, just a couple of minutes. As that happens, we can look for atmospheric absorption signatures from sulfur dioxide, and we see that the atmosphere collapses, although not quite all the way. It's not collapsing fully to that extent of a factor of 1,000,000 where this would just disappear. We still do have some sulfur dioxide in eclipse, just not very much. This sort of gives some hints that maybe what we're seeing is a volcanically supported atmosphere. So this is good evidence that most of the atmosphere is supplied by sublimation, and we're just evaporating it off the surface. On the other hand, when Io comes out of that shadow and gets exposed to sunlight, it's going to heat back up really quickly. And we should see the atmosphere puffing back up if it's created by sublimation. And these data points are pretty much flat, whereas the model predicts that should puff up a lot. So we've got two directly conflicting pieces of evidence here. These are contradictory results. The fact that it partially collapses and doesn't collapse by a factor of 1,000,000 suggests that maybe both are going on. And that's sort of a rare coincidence in astronomy. Usually something dominates by an order of magnitude or 2 or 3. You very rarely have things that are working in competition in terms of supply and loss, like we have here at Io. So I've sort of taken the initiative to try and understand how Io's atomic atmosphere is responding to these eclipses. The molecular response was sort of shown by other people in the field around 2015, 2016. I got inspired and I went to the telescope and tried to figure out how the atomic atmosphere is responding. That's not so obvious what it should do, right? It's not in vapor pressure equilibrium where it's evaporating off like sulfur dioxide. It's sourced from the sulfur dioxide, right? We need to create those atoms from the molecules to begin with. And how quickly does that chemistry happen is sort of what we're trying to learn about. The reason it hadn't been done before was it's really hard to point the telescope, right? If you're in Io's penumbra, we can still see a little bit of light. You can know where you are, but the moment you cross into shadow, you better have really good tracking. And of course, you're moving it around the sky like this. So you need to have a good refraction model at the telescope. And I've had to throw out maybe half the data or so because I was just pointed in the wrong place. And ultimately, I gave up on refraction models and decided that pointing moon to moon with non-sidereal tracking rates was the way to do this experiment. So that's kind of the difficulty of why it hadn't been done before. And then when we finally got the answer of how the atmosphere responds to eclipse, it was really surprising. In orange, we have sodium emission, and that probably comes from the molecule sodium chloride that's been seen in Io's atmosphere. But sodium chloride doesn't condense the way sulfur dioxide does. When it gets cold, it doesn't, turn into solid state or liquid down on the surface. It should still be in the atmosphere. It's not removed. And yet, the collapse from sodium is even more rapid than this collapse in blue that simultaneous measurements with ALMA made in sulfur dioxide. So this was an unexpected result where portions of the atmosphere are collapsing that shouldn't. On the other hand, this oxygen emission here in red is sourced from sulfur dioxide, right? That oxygen atom is coming from a sulfur dioxide molecule. So we expected that to collapse. Two different eclipses, one time it gets brighter, one time it gets fainter. So what the heck is going on with oxygen? It's totally odd, and it's decoupled from sodium. So this was all surprising, and we needed to sort of figure it out, and we're still sort of trying to piece it together. You can also look at sodium in sunlit emission, and now we're exciting those sodium atoms with light as opposed to electrons. And so it's bright, and you can see it. And when I map out exactly how bright it should be, it increases by more than it should just from geometric considerations. So it's moving to the right on this diagram. That column density is increasing, and we can see some saturation effects happening here, right? If you increase the column density, you're not just increasing that emission linearly anymore. You're starting to become optically thick and saturating that emission. So a little bit of increase in brightness corresponds to a big increase in the column density. And we think sulfur dioxide is collapsing by about a factor of 3 or 4. It turns out the sodium emission, because of the saturation, is collapsing by 10-fold. So the working theory that we have for this so far is that this is ionization of the sodium chloride molecule, NaCl, by sunlight. And you would think, okay, there's a lot of electrons at IO, maybe those electrons would ionize, but we need it to respond to flipping the switch of turning off the light, going into eclipse. And we need that to happen quickly. So this is kind of, coming back to basic physics of we did an experiment that is light is the only independent variable, and we got a response, so therefore light must be the driver here. So eclipses could interrupt the ionization of sodium chloride, table salt. And now we don't have any more NaCl+. Molecular ions like this combine really quickly with free electrons. This happens almost instantaneously. And so if you switch off the supply, all of those get exhausted pretty rapidly, and you don't have any more supply of atomic sodium if you get rid of that ionic pathway to generate it. So now we've got this neutral atmosphere. It has interesting properties with atmospheric collapse. It's volcanic and it's dynamic. What happens when all of this gas is ionized? If we're on Io here and we have a neutral atmosphere and it's exposed to sunlight to create an ion of NaCl+ or some other ionized gas, that gas is going to feel the magnetic field of massive Jupiter. And Jupiter rotates with a 10-hour period. Io rotates with a 42-hour period. That means that the Jupiter magnetosphere is sweeping past Io pretty quickly. We subtract off this 17 km/s orbital velocity from this co-rotation velocity, 74 km/s. It means the plasma is smacking into this moon Io at 57 km/s. Where is it coming from? It's the ionized material that got trapped in Jupiter's magnetic field, did one orbit around Jupiter, and then recollided with the moon. So when you ionize that gas, it doesn't orbit around Jupiter, collides back into Io, that ionizes more gas, goes around Jupiter, collides again. You get positive feedback into the system. So it has sort of a runaway effect in generating plasma. That plasma is interesting kind of in and of itself because it has this odd velocity distribution. All of its energy is coming from that co-rotation velocity. And so it has this ring distribution in velocity space where the gyro motion is all perpendicular to the magnetic field. And it's not until it has some time to sort of thermally equilibrate from Coulombic collisions in the plasma that the temperature becomes something more sort of reasonable and evenly distributed. And so that's what makes the red stuff here in this picture. Jupiter's magnetic field is blue, and that ionized gas coming from Io here is spreading around in this wobbly donut because Jupiter's magnetic field is not perfectly aligned with its rotation axis. That little tilt makes the whole thing wobble. And it lights up at different wavelengths. So we can see it in the ultraviolet and we can see it with the visible. And it has this interesting structure to it. Plasma Torus. At ultraviolet wavelengths, the albedo of the planet Jupiter and the moons is really faint. So we don't see much reflected ultraviolet sunlight. And you can just take pictures of the torus, take cool movies like this. The little tick mark shows one Jupiter longitude at a fixed position. You can watch the whole thing rock back and forth as Jupiter orbits. In the optical, at visible wavelengths, this is red wavelengths, if you want to image this stuff, it's a lot harder. And that's just because Jupiter is so bright and the moons are so bright. So the trick to do this is to take a sulfur filter that just looks at ionized sulfur and put a mask down the middle of your detector so that you mask out all that bright reflected sunlight from Jupiter. And then you image the torus red, but you still have these pesky moons moving in and out of your field of view. And they sort of outside of you just view. So it's hard to get good pictures of these things, but the pictures are really cool because this is the only way that we have to take a picture of a planetary magnetosphere, right? So we think lots of planets have magnetospheres, but this is the only way that we have to actually kind of have it. In the visible and in the ultraviolet and in the visible, there's pretty different properties, right? This doesn't have a whole lot of like spatial structure, but we see a lot of spatial structure here, right? This ring sort of comes into a long ribbon-like feature here, where the temperature increases. And why do I say the temperature and sort of do this? Well, if you think about being on a magnetic field line as plasma around a rapidly rotating Jupiter, that centrifugal force is going to pull you up to the furthest rotation along the magnetic field line that you can see, like a bead on a string. But if your plasma on that bead, on that string, increases in temperature, that temperature is going to push you in latitude and sort of distribute you along the magnetic field line. So the plasma temperature here is hotter than the plasma temperature when you have just a narrow range of latitudes in the plasma torus. So you can learn about plasma temperature that way. And the temperatures here are pretty low. This is a couple of electron volts in the optical, and you get different structure in the ultraviolet just because you need hotter electrons to excite those emissions in the ultraviolet. So we did the biggest survey yet of iris emissions in the optical, and the other motivation for this is that we wanted to time it with a JAXA satellite called Kasaki. NASA was sort of missions, they have a big projects that almost all these units to different planets, and they try to do a whole bunch of studies at once. NASA would never build a telescope like Hubble or JWST to study one object, but JAXA is very good at going after just one niche specific target and doing it very well. The Japanese Space Agency built a spacecraft orbiting around the Earth that just stared at the plasma torus in ultraviolet wavelengths for years and years. And this was the first data to come back down. They have a spectrograph slit that's oriented across Jupiter. And this is the ultraviolet spectrum on both sides of the plasma torus here. That's the spectrum of Jupiter down the middle. And that's Aurora on Jupiter that they're seeing with this. In the optical, we don't have the luxury of Jupiter being so dark, so we needed to mask it out. So I took a strip of neutral density filter, put it across the spectrograph slit, and that stops down Jupiter in the middle. So you still get Jupiter light, but you can use it for a reference to figure out exactly where they're pointing by having that spatial reference. And we know how much light Jupiter reflects. That also helps calibrate how much flux you're getting through the telescope. The lines that we see from all these are derivative of sulfur dioxide originally. We've got singly ionized oxygen here. There's a bunch of different charge states of sulfur here in the ultraviolet. And we have singly charged oxygen, twice ionized sulfur, and sulfur over here light up in the optical. And when you observe for 5 hours, thanks to Jupiter's 10-hour rotation, if you're looking at both sides, you can map out the azimuthal and radial structure of the plasma torus. And it changes. We see bright spots sort of come and go. We see that sort of collapsed cold torus region that is interior to this come and go and change its brightness. And this dotted line here shows where Io's orbit is at 5.9 Jupiter radius. And if you notice, the emission on one side is well interior of that, and emission on the other side is not. So this whole plasma torus seems like it's offset. That's a typical day. Some days look like this. So this is one side of Jupiter that's really flaring, very bright. On the other side of Jupiter, we don't see anything at all. Now the geometry is fixed, right? It should be there, it's not. So there's brightness asymmetry between optical. Those are very dynamic. In the ultraviolet, this brightness asymmetry was known from the Voyager spacecraft. In the early 1980s, when they did an approach to the Jupiter system, they stared at the plasma torus and saw that it was brighter on one side. And then when they left the Jupiter system to get that gravitational assist and head on outwards towards Saturn, they looked back and they saw it was still brighter on that side. And so they used that sort of stereo geometry and said, okay, this is a fixed local time of Jupiter where it's just brighter on the dusk hemisphere all the time. And it wasn't immediately understood why. There were two papers that came out a year later that gave the explanation. And it's that there's an electric field that shifts the whole plasma torus sideways towards dawn. So plasma torus isn't centered on Jupiter. It's a wobbly donut that sort of does this and is kinked over one direction. And the question is, what is this electric field that you need to shift the whole plasma torus towards the dawn sector or the dusk sector? It's shifted towards dawn, and it's brighter at dusk. Now, if we think about what's causing these emission lines, it's plasma, where electrons are colliding with ions. And if you take that plasma and push it towards the planet, the magnetic field is going to get stronger then, right? So you compress the plasma, and there are more collisions consequently. So it's brighter at the dusk hemisphere in general for that reason that is offset. We've compressed the plasma adiabatically into a denser magnetic field. But we don't really know if that's plasma density or temperature that changed, right? Those two things are often degenerate. In the visible, we can just measure that offset, right? We don't have spatial information in the ultraviolet, but in the visible, you can look and see where the plasma torus peaks. And the peak on the dawn side of Jupiter, Jupiter's local dawn, is farther away than the peak at the dusk side. These are the magnetic field lines of Jupiter mapped onto that torus emission. So there's this asymmetry in radius where the whole plasma torus is shifted towards the dawn sector. And then as Jupiter rotates, the plasma torus also wobbles this way. It sort of shimmies back and forth. Why? Well, we would think that it tracks the magnetic fields, and if Jupiter's rotating really, really fast, it's going to do the bead on the string thing, where it's going to go the furthest distance it can on the magnetic field. That would track out this sort of dotted line here and the black line here. And so the wobbling is a wobble, but it's actually less than we would expect from the magnetic fields. No explanation, no theory has yet helped us understand why. This offset that's pushing the whole plasma torus sideways towards this dawn side over here corresponds to an electric field that does match the ultraviolet data, but we don't know whether that's an increase in density or temperature that's driving that emission. And the scatter here exceeds the error margin, right? So these are real changes where if you come back and observe it the next day, it'll just be different. It won't always follow this trend. Say a volcano goes off on Io, it might shift one way or the other. In any case, due to the geometry here, Io here at 5.9 interacts with a much more dense plasma than does Io over here at dusk. And due to this wobble, that happens to occur at about 130 degrees longitude on Jupiter. So there's specific geometry where Io encounters the densest plasma that Io is generating. One thing that came as a surprise is, okay, we just talked about the motion of this feature right here. There's also this other plasma interior, and there's a gap between those. As Jupiter rotates, we can watch Jupiter longitude go by here. This is Jupiter's longitude, 0 to 360. The latitude of those two things with respect to one another changes, and the gap between those things with respect to one another changes. And these aren't big changes, 0.1, 0.2 Jupiter radii as Jupiter orbits, but those size scales are really large in comparison to tiny moon Io. So it changes the conditions that Io encounters in that plasma quite a bit. And just like the wobble itself, there is no theory for this observed phenomenon. We don't understand why. So here's that emission mapped out in a radial profile. Here's this dotted line showing where Io's orbit is. You can see the dusk side interior to that and the dawn side pretty much hitting that. If I take all of that data and correct for this radial wobble, I can take out the wobble and the emissions get a little bit brighter now that I've co-added data using sort of a fixed radial coordinate, tracking the torus. And we've got all of these different emission lines that light up from different charge states of sulfur and oxygen to work with. This equation here that I showed and didn't explain, this is the brightness, and that's the integral over the line of sight of an Einstein coefficient for spontaneous emission from an upper state J to a lower state I, times the fraction of ions that are in that upper state. This fraction F of J is dependent on the electron temperature and the plasma temperature of the electrons, NE and TE, times how many ions are there along the line of sight. And because of this fraction right here having different cross sections at different temperatures, different densities, we can map out line ratios into plasma density space and plasma temperature space. And given line ratios of these emissions will fall somewhere on that diagram and uniquely depend the plasma patterns. But even though we can't see the electrons, because of how they're exciting the ions, we know what their properties are. And this is all a nice theory. We're really excited and going to try to do it in practice. Really messy. The plasma density is here in black. The plasma temperature is here in red, and I've overlaid those. And it didn't make for pretty plots, but there was some really interesting stuff in there. This inner peak right here, it shows up in the red sulfur lines. It doesn't show up at the other wavelengths. And these are long wavelengths. These are short wavelengths. So long wavelengths have lower energy needs to excite them. They can be excited by 2 electron volt plasma down here, but the other lines can't. And so that's why the line ratios tell you that the plasma temperature there is very, very cold in the inner plasma torus. If we move to the outer plasma torus, out here we get temperature around 4 electron volts at the density peak there. But remember I said that there was this certain geometry where the torus would hit Io? That's right here where the dotted line hits the plasma torus there. And we see the temperature there is really low. This is probably where we're creating fresh plasma and feeding it into the torus is on the dawn side. And probably at the dawn side at specific longitude. So we're able to get something. It's a messy plot, right? It has some problems. Here we've ignored the fact that we're looking at a disc-shaped object along its line of sight, right? The stuff in front of the peak of the emission is sort of contaminating the data here. So what do you do about the effective path length? What kind of an assumption do you make with that? An alternative here is to take spacecraft data and then use it to hack the telescope data. That's not entirely self-consistent, so you have to sort of state that up front. But it does combat this line of sight effect. And so what I did was take the plasma temperature from the Voyager PLS flyby through the Plasma Torus, the only spacecraft that has flown through it so far. And I used that to set that point in the diagram and then compute from these line ratios what the electron temperature and density is. Sorry, just the electron density. And I get about 4,000-ish per cubic centimeter here, 3,000 and change on the Dawn side. One is more dense than the other. And they're slightly offset from where the emission peaks are. Here's the Voyager calibrated measurement of their density on the dusk sector. And I think that the optical data now it shows that the torus is actually more dense than we thought way back in the 1980s. There's a third technique, which would be doing that line of sight integral across the different temperatures and densities as a function of radius. And we call that an Abel transform or an onion peeling technique. That's messy, and I haven't gotten to it yet, so it's TBD. So you'll see on the dusk side, there's these bumps here that are outwards of the Plasma Torus. What the heck are those? Are they noise in the data? And I tried to get rid of them, because I thought they were noise in the data. And then I started looking more closely, and there are these ripples here in the outer Plasma Torus. And if you see a ripple in one line and not another, it's not some artifact of your telescope like a flat fields error or something along those lines of a systematic error. It's real in the data. And if I look, these things rotate in and out of the field of view as the Plasma Torus rotates. So that's pretty cool. We have these sort of ripple effects of density propagating in the outer Plasma Torus. And they're transient. We think that it's interchange. So hot flux tubes are trying to get outwards in radius, and cold dense flux tubes are trying to move inwards. And those two things swap places. And where they swap, they interchange. And this interchange could give you these sort of ripple effects. That's one theory. But again, hadn't been seen before, no good explanation. There's also this sort of periodic change in brightness. So if I just look as Jupiter rotates and say, how bright is the Plasma Torus? It has periodic enhancements at certain longitudes. And that's seen both in the ultraviolet over here and the optical data over here. My first inclination is like, okay, we've got this wobbly donut of plasma. Maybe it's sort of an edge-on versus face-on effect. And if the torus is wobbling, maybe I'm getting less of a column density when it's open versus when I'm doing it edge-on. Doesn't work. That would happen at a different longitude. That's not a line of sight effect. So at 200 and at 20 degrees, we are viewing the torus edge-on. That's when you should get the peak column density. But the brightest emission here is offset by 70 or 80 degrees longitude from that. So it needs an explanation, right? Why is it brighter at certain longitudes? And I tried playing with a bunch of things to figure out why, and I still don't really have very good answers. I have some loose correlations and sort of qualitative remarks that it corresponds to things that we see in other data sets where it was not explained. So if I look at oxygen emission on Io itself, that sort of has the same structure here, where it's brightest at 120 and at 300. And I've just folded two longitudes together here, so wrapped it through 720 so you can see the periodic structure better, where it's not interrupted. So those bright things happen in data of Io's emissions right on Io itself here in oxygen, and they happen here in the torus. What's the driver? What's causing that modulation in longitude? Well, if it were plasma density, if I view the plasma density of the torus from a model based on Voyager that we built, Io is passing through all of these different regions, and so the plasma density sweeping past Io changes as Jupiter orbits. And that's this plot down here corresponding to the dates that I actually measured. They don't correlate very well. It's kind of a scatter plot. If I consider another effect where maybe it's the distance between Torus. And when it last swept past Io in magnetic coordinates, that's a mouthful of geometry. The distance between Io and the Dawn and Dusk sectors in magnetic coordinates is this sort of separation in L cell, we call it. And that's where Io's encountering the densest plasma. If I plot that here, that's a better correlation, but it still has a lot of scatter. Maybe that's just the best we can do, right? This is a volcanic moon, but it has all sorts of activity. So you don't necessarily expect the best correlations to come back out. And maybe that's just sort of what we get. And there are additional periodicities in the system that haven't been accounted for that muck all this up. So that's sort of the working theory, but again, we don't really know. You do see this structure in another place, and that place is a footprint in Jupiter's Aurora that magnetically maps down to the planet. So as Jupiter rotates, this footprint of Io in Jupiter's Aurora, as a function of Jupiter longitude, changes its brightness. And what the heck am I talking about with a auroral footprint on Jupiter? There's a video here that shows Jupiter's Aurora, just like Earth's Aurora. And this feature right here, it sort of looks like a comet that's coming out from the right. That's a magnetic field line that connects Jupiter's ionosphere to Io's ionosphere as one big circle. If we follow the magnetic field line from Io to Jupiter, it maps to the poles on Jupiter through this kind of system. So we've got Io with an ionosphere as a conducting bond. It's moving subsonically through a magnetic field that is Jupiter's magnetic field. And when you have a conducting object in a moving magnetic field, it generates a current, and it generates Alfvén waves. We've perturbed that magnetic field by passing it through a conductive body, and that drags the magnetic field line. The magnetic fields they're sort of like rubber bands, and if you bang on them, they have resonant waves that pop out. Those are called Alfvén waves. The Alfvén waves that are generated from the torus sweeping past Io, that magnetized plasma getting distorted, leave Io in two directions that we call the Alfvén wings. And those Alfvén wings are waves propagating in latitude in each direction. And like all waves, they can reflect and refract. And waves reflect and reflect whenever they encounter a density gradient. The torus itself is a density gradient. So these waves propagating from Io can, at some angle of that Alfvén wave propagation angle of the bent magnetic field, propagate downwards until they encounter a different kind of plasma away from the plasma torus. It's more rarefied, big enough bend at that interface there, and refract. And that brings them down to one location in Jupiter's Aurora, or another location in the opposite hemisphere, depending on how far they had to travel before they bent. So we get these spots in one hemisphere and another that are in different locations. But then some of those waves also bounce off of that interface with the plasma torus, where we go from dense plasma to rarefied plasma, and they refract, reflect and refract. So we get these bounces that are moving across the plasma torus, and some of that gets through, and we get multiple spots. Before the Juno spacecraft arrived, we knew about these spots, and we knew that they were complicated, and we can also have some electron beams that are going hemisphere to hemisphere, communicating across the plasma torus. There's all this complicated wave structure that's bouncing and reflecting and refracting. But here's the footprint viewed right from above with the spacecraft. We can see that there aren't just 1, 2, 3 spots, there are dozens. And these waves really do propagate in the plasma torus for a very long distance downstream. And here's the crazy movie that shows the geometry of all that. So the plasma torus is wobbling, Io is fixed, it launches these Alfvén waves, the alphane rays either reflect or refract at that boundary, and then that maps along the magnetic field to Jupiter's poles and gives it a little footprint in the aurora. And the interspace of the different spots in there just depends on longitude and the Plasma Torus, Jupiter's longitude. So this is a circuit, right? This is the flow of plasma coming in this direction, and the plasma is going to be diverted around this moon Io. So we're going to increase that plasma. There's a gradient there. Just that can create electric fields. But then there's something called the Hall effect, where it's easy to deflect the electrons. It's very hard to deflect the ions because they have so much momentum. So you can't bend those nearly as much. And the ions collapse and sputter into the moon where the electrons are deflected around. That generates a much stronger electric field. So the Hall effect causes an asymmetric plasma precipitation down to Io through Io's atmosphere. This fact that more plasma is precipitating in one hemisphere than the other is what drives this whole current system of a circuit. And the bent magnetic field lines that then map down to Jupiter's poles are these distorted field lines here. The circuit goes both ways. So we have currents running into Jupiter's northern hemisphere and into Jupiter's southern hemisphere. And where they close here is where the most bending of those flux tubes occurs at Io's equator. And Io's aurora lights up the circuit path. So at Io's magnetic equator, you get two auroral hotspots. This is seen in Eclipse from the Cassini spacecraft. Took images of Io in Jupiter's shadow on its way out to Saturn when it was getting its gravitational assistance from Jupiter's sort of guided shadow. And so you can see at the very end, Io is coming back into sunlight. You can see sort of a crescent moon. Now, where the plasma is tangential to those field lines, and we're closing that current in this big circuit loop, that's where we're driving the most plasma into Io's atmosphere, and that's where it lights up. And so as the orientation of Jupiter's magnetic field rocks back and forth due to the tilt of the dipole, these field lines change where their tangential points are on Io. And so we get this rocking motion here of these two hotspots of aurora on Io. The latitude of those two spots doesn't rock as much as it's supposed to from the magnetic field lines. It's a little bit less. And that little bit less comes from induction. Induction is this force that tries to resist a change in the magnetic field. And we're changing the magnetic field just by changing its direction. That oscillating magnetic field of Jupiter has an induction current that is trying to resist the oscillation and force it back. Induction happens whenever you have a large amount of material that is conductive inside of a planet. You get induction currents that fight the changes in the magnetic field. And so this raises an interesting question. Is what is causing this conduction, what is causing this induction current a subsurface magma ocean that is conductive? Or is it a conductive metallic core inside the moon? We still don't know, and people argue back and forth. So this is a cool movie that I like to show you. What is all this? This is the Cassini imagery burning this flyby Jupiter system. And we've got a bright spot here. That's actually a volcanic plume showing up in near infrared wavelengths. And this is, if we stack up all of the clear images and take a time series. But Cassini also had all of these filters all the way from the ultraviolet down here into the near infrared over here, meant to take pretty pictures. And those filter bands, some have emission in these bright hotspots, some don't really. And it's bright in some places and not in others. There's a lot of different emissions at different wavelengths. And many of these remained unexplained. So this is sort of one of the things that motivated me to try follow-up spectroscopy, trying to figure out what these emission lines are. I already mentioned that sodium was one of them. You can see in red here is when Io is hottest in sunlight. As it goes into Jupiter's shadow and its temperature collapses, the sodium emission collapses with it. So if I take all that scattered Jupiter light in the spectrum here, this is Jupiter's reflected sunlight. This is sodium gas in the sun's atmosphere that is giving you this absorption line. Once I subtract off all that Jupiter scattered light, I'm just left with the auroral signal from Io, and that auroral signal changes pretty quickly. Io's sodium atmosphere collapses after it enters into eclipse. So the working theory for this behavior is that emission is tracking the ionization rate of the molecule. That's sunlight that's ionizing the molecule. It was not clear at all what all of these emissions in the infrared were. I was able to pin down one of them, and here's the spectrum out here at wavelengths that are just redder than we can see with our eyes. And it was only after co-adding all of these exposures with the Keck telescope that I was able to get a little blip here and a little blip here. And that's the first detection of a potassium aurora that's been seen anywhere. So it's kind of cool that we just have a potassium aurora on Io. But because I had to co-add all of that data, I lost the temporal information. We don't know how Io's potassium aurora changes over time, the way we do for sodium. And the brightest emission here is oxygen 6300. Remember, red is right after ingress into eclipse when Io's surface is the warmest. That's actually increasing in time. So as Io gets colder, its aurora gets brighter. What the heck's going on with that? Remember, we have an oscillating plasma torus, which is precipitating a different amount of plasma onto Io and generating a different brightness of aurora coming back off. So the emission and oxygen wavelengths is just tracking Io's location in the plasma torus. And that's what had that funky behavior on the earlier plots that I showed. I looked with Hubble and tried to understand how the ultraviolet aurora responded to eclipse. And it basically doesn't. It just tracks the torus emissions. The torus lines are here in dotted blue. The neutral lines from oxygen and sulfur and chlorine are seen responding to eclipse. This is sunlight going through ingress. Now we're in shadow. And there are changes, but the changes are proportional to what the torus changing plasma is doing. So it's not responding in terms of like the atmosphere is collapsing or changing. It's just getting brighter because we're pumping more electrons into it. And that's all fine and good, but remember what we were saying earlier, that our working theory is sodium chloride ions responsible for the sodium collapse. Well, chlorine should collapse in eclipse if sodium collapses, right? You can't have one without the other. So that was a mystery. The mystery got solved with quantum mechanics. This is the oscillator strength of the emission for a whole bunch of different lines in the ultraviolet from oxygen and sulfur and chlorine, all atomic neutrals. And if you have the same upper state of these transitions, they should radiate proportional to their Einstein coefficients, their quantum mechanic Einstein coefficients that say how long it takes for a photon to leave the excited atom. And you can take the ratio of emissions that share the same upper state. That gives you a predictable line ratio that comes back out the bottom. And now I've sorted it here in terms of very inefficient emission down to very, very efficient emission here, where it only takes a nanosecond, 10 to the negative 9 seconds for that photon to be radiated by the excited chlorine atom. It wasn't until sort of around here that a pattern emerged where the predicted ratio for these lines sort of matches what it's supposed to match until you get to the efficient emissions, and then we see it diverge between what you expect if this is an optically thin emission versus an optically thick emission, which is saturated. It turns out that the chlorine lines are all heavily optically thick. So even though they're faint, they're saturated. And no matter how you change the chlorine atmosphere on Io, you'll still get the same brightness out. So that's why sodium changes, but chlorine doesn't, even though they both come from table salt sodium chloride. Now, so far I've just been talking about the torus and the atmosphere right around Io. that interaction between Io and the Plasma Torus generates these big extended neutral clouds. And this is kind of a cool amateur astronomer thing. You don't need big telescopes to go and study this. This is McDonald Observatory, and it sort of looks like similar setups to what some people have in their backyard around these parts. This is a 16-inch telescope with a 4-inch telescope attached to it. They just have nice instruments on the back. These are bright planetary objects, and so you don't need big glass to do science like this. Now, if we take a sulfur filter and a sodium filter and put a neutral density strip across the middle, we can watch the plasma torus in one filter and sodium behavior in another. And as this plasma sweeps past Io, which is this moon right here, it's driving off a jet of atomic sodium that flies off tangentially. So if you view the system from top down, here's Jupiter at the center. Plasma torus is sweeping past Io like this, and when it impacts Io, it throws off a jet of neutral material. Kind of cool. And the way that we're sort of studying this jet, this interaction that we think is going on, I was using to explain the collapse of sodium is this recombination right here. This ion is going to have felt Jupiter's magnetic field. So that's moving 60 kilometers per second. If I neutralize it, I'm going to see a fast, energetic neutral fly away from Jupiter. And lo and behold, there they are. So that's all this little tiny chronographic imager, 10-centimeter aperture telescope, just with a special filter in it. We also have this co-aligned spectrograph with it that is kind of this wicked, complicated beast. But it's still, not too far out of the range of what some amateurs use. What we've done here is take a matrix of lenslet arrays. Instead of putting a detector at the telescope image plane, we've put a bundle of fiber optic cables in a matrix here. There's a 20 by 20 matrix, and each one of these lenses focuses those light into the fiber. And if I multiplex those fiber to one row to pass them into the slit of a spectrograph, now I can get a spectrum for every pixel that this image takes. It's called an integral field spectrograph. And after I unwarp that data and process it a little bit, it looks like this, where we've just got hundreds and hundreds of spectra at different spatial locations in the image. Here is scattered light from Jupiter that corresponds to one Doppler shift, and we get another from scattered sunlight off Io, which has a different Doppler shift with respect to Jupiter. And then the emission has a different light path that just goes Io to Earth. Reflected sunlight is going to go Sun, Io, Io, Earth, and that's a different Doppler shift. So kind of busy here, but we've got two different sodium features from absorption. Both are actually sodium in the sun's atmosphere, and one sodium emission, and they're all separable by Doppler shift. We can use that information to get rid of all the scattered sunlight. We're left with the emission here just from Io. There's a lot of residual noise when you're looking right at the moon Io itself. But we have these two populations, slow sodium and fast sodium, that we think is coming from this reaction where we're neutralizing the ions using that fast ion speed and giving it to the neutral sodium coming back off. And it's moving really fast. That's 75 kilometers per second where the dotted line is, and we still see emission above those velocities. You put all of that back together and make a map of what that sodium emission is local to Io. And we see that there's these features coming off in one direction and another. Some of it is leading Io in its orbit, and some of it is flying off tangentially away from the system completely. And at the opposite location, sometimes it flies off at a pretty odd angle. If I then separate by Doppler shift and just look at the fast stuff versus the slow stuff, I can separate out stuff that is coming from this ion recombination reaction, really fast sodium flying off tangentially, versus the bound atmosphere that's generated by sputtering. And that has a different distribution. That's kind of cool that I can, just look at two different atmospheric processes by separating through Doppler space. But then we asked an interesting question, well, what happens when this fast jet of stuff that's spewing out, up to beyond 75 kilometers per second hits the adjacent moon that's next door to Io, right? There are other moons in the system. We're beaming out the atmosphere of this one moon. What happens when it hits another one? There's a resonance in the orbital period between Io and Europa. And so it's just the longitude difference where you can predict where the stream would jump moon to moon. This is Io here, this is Europa here, and this is a scaled down image where if I scale it up here, I can now see this jet coming from Io and interacting with Europa's sodium atmosphere. There's sodium on Io, sodium on Europa. We think sodium on Europa actually has pretty interesting origins. Remember, Europa is our ocean world. Oceans have salt water. That salt is mixing with rock. So the question here is Io contaminating Europa with its salts? Or does that salt come from Europa's ocean? So when this jet sweeps past this other atmosphere of a moon, we can take a picture of this phenomenon with this instrument using the Doppler shift, and with the geometry try and work out how much sodium is being transferred moon to moon. And it gets messy, but it still works out nicely where the only degeneracy here is this factor Z, that is, we don't really know what the column along the line of sight is. We don't know how thick this jet is. But if you make some reasonable assumptions there, what you come up with is about 10 to the 25 atoms per second leaving the moon Io, landing on Europa. And that's an order of magnitude below what atmospheric escape models predict just for what Europa loses in any given second. And that's a steady state escape rate. So even when you have the most transfer moon to moon, it's not enough to supply Europa. And so Europa's sodium atmosphere is coming from Europa's ocean. It's not contamination from the moon Io. We are learning about Europa's salty subsurface ocean, and we're studying Europa's atmosphere. Back to this image of the torus that's generating this jet. If you look at the Doppler shift upstream and downstream of Io, you can say, okay, there's definitively a jet of neutral sodium flying off fast here and not back here. Now let's ask the question, well, we have oxygen and sulfur emissions that we can see with Hubble Space Telescope. Do those have similar jets? And they do. We're delighted that if you co-add all of the oxygen and sulfur lines, the ultraviolet, and co-align them for the expected Doppler shift, and you point your Hubble Space Telescope on Io and then off Io in the direction that these jets should be going, you do see the Doppler shift. And there are fast jets of sulfur and oxygen coming from some sort of neutralization reaction where we've taken an ion that is moving at fast velocity and neutralized it into a neutral atom. So it's noisy, but it's there. And it has big implications. So remember that little tiny coronagraph that I showed you? It has a really big field of view. This is 7 degrees of sky. And so the Pleiades would fit in just a tiny portion of this image. It's a really big field of view. And we're masking out Jupiter in the center with our neutral density. That's the trick that I've shown a couple times now. If you take an image at sodium wavelengths and an image just off bands and scale and subtract those two, you see this massive nebula of sodium atoms that extends for multiple degrees of sky. The sun's only half a degree of sky, right? This diffuse cloud of atoms that are flying off from this one chemical reaction on this tiny moon Io is filling up an area of the sky this big, right? It's huge. So this is one of the largest objects that is known within our solar system. Diffuse cloud from this one chemical reaction on Io. And now we know that there are diffuse clouds of oxygen, diffuse clouds of sulfur that are there because we've measured the Doppler shift, we just haven't seen them in a nice image like that. When a volcano goes off, this volcano maze, that whole nebula lights up. And we can measure the sodium cloud response to volcanoes, changing their brightness in response to when the volcano goes off, it takes a few months of time for that cloud to light up and then dissipate. It's kind of cool that we can, watch the chemistry change when there's a new volcanic plume on Io. And you can do the same thing in the Plasma Torus, where you monitor what emission from 3 times, 4 times ionized sulfur is, and things like that. And the Aurora on Jupiter gets excited by all of this activity in the Io Plasma Torus, because remember, there's a circuit going back and forth between them. So there's a lot going on here, right? Io is kind of one of the most interesting objects, if not the most interesting object. We've got volcanoes, we've got a collapsing atmosphere, we've got a plasma torus, auroral footprints and spots that change their interspot separation. We've got a jet beaming from one moon to another moon on Jupiter, sending its atmosphere from one moon, and that atmosphere gets collected by another moon. And we've got these vast clouds of, now we know, oxygen and sulfur that are more big in their size scale than the size of the sun to the moon on the sky. Really big diffuse clouds that come from all these reactions. So it's an interesting place. Thanks for walking through it with me. I had a really nice time visiting it. Would really love some questions if people have them. Yeah. Yeah, so the question is, can you collapse the rings of the plasma torus? Yeah. The rings are driven by Jupiter's rotation, right? That's the bead on the string thing. So if you collapse those rings, you stop Jupiter from spinning. And that's hard to do because it has a lot of momentum and it's really big. Other questions? Uh, 4 inches, centimeters. Accurate stuff easy to do, just think of a really expensive filter that has a very, very narrow band pass to sulfur. For just single transition to sulfur. Get a mask out for you. So the question is how wide a filter? The sodium lines are 6 angstroms apart, and so 1 nanometer does it nicely. The sulfur lines are more like 15 angstroms apart, so that's why there's more background scattered in those images. You got a question up there? Yeah, so the question's about the exchange of an atmosphere from one moon to another. What's the travel path there? It's like you have an outward moon and an inward moon, Io, and if you just launch something tangent to the circle, where does that straight line go? Does it intersect the other moon? Okay, now you've exchanged an atmosphere from one to the other. You follow? Okay. Other questions? Yeah, so the question is, if you have drastic changes on Io and you're moving Io's atmosphere onto Europa, would it have big changes on Europa? And no, because with those equations in the geometry, you can compute the flux of how many atoms are coming from Io and landing on Europa. It's pretty tiny compared to what's just escaping Europa. And just from a mass balance, from continuity, if you have a tiny amount coming in, but a lot coming out, it needs to be coming from Europa itself. And so any changes in Io are a drop in the bucket compared to Europa itself. Other questions? I thought I saw one over here, maybe. Yeah. Yes, but only real close to Io is it important, right? Once you get up to about 100 kilometers or so, which is the altitude of where volcanoes are lofting their plumes. Yeah, at the surface, it's nanobar-ish, where 1 bar is on Earth, so 10 to the -9, 1 billionth of an atmosphere here. It's pretty rarefied, but it's denser than the other moons. Yeah. Up there.
Your atmospheric exchange between other large foods.
If there is, it's awfully hard to observe, and so we just don't know. We think that Europa has a torus. It's a paper that is in review right now, where they discovered an H2 torus, molecular hydrogen, around Europa, and it makes a full toroidal shape, just like the Io Plasma Torus. Juno spacecraft has just discovered that, but we really haven't characterized it very well yet, and you certainly can't see it with ground-based telescopes like all this stuff.
So we thank you very much for coming in this evening. Again, please join us on April 1st, 7:30. We'll have Dr. Aaron Cox here from Northwestern University, learn about planet formation. Have a good weekend, everybody. You're fine. Yeah, no problem.
Thank you. Take care. Thank you very much. It was one of the currency time conservation things. It's like one of the first things they're going to look at. Yeah, I'm looking forward to it. Yeah, it's a big cool new stuff to learn. One of the first ones. Yeah, they had to give it for saying that it's kind of basically prescribed like Jupiter.
Thanks for coming, Woodrow. See ya. Thanks for joining us tonight, everyone. Take care. Have a good weekend. Join us again on April 1st to hear from Dr. Aaron Cox about planet formation. It should be really great.